this is one of good assumptions of or what should be in place for you to use OLS. For you to use OLS, you must ensure that your model is correctly specified. If the model is not correctly specified, you may find that your results may not be very good. So if your model is not correctly specified, we say the model is misspecified. But it's not easy for you to get the right model. That's why sometimes we should say it is like getting the right model is like searching for a black cat in a room that there is no light. You see, we cannot know where it is. So in other words, we are simply saying it is a tall order to get the right econometric model. So it's like somehow trial and error, isn't that? So what we can do, we can look at some of the things you can check to ensure your model is good. So we call it a model specification criteria. What can you check to ensure that your model is good? The first you can do is the model should be data admissible. By data admissible, we are saying it must make some logical meaning. You see, after carrying out your regressions, the results you get, are they logical? So if they are logical, it could be one way of saying that your model is good. Also, is the results consistent with the theory? Like, for example, you know the theory of demand. For example, if the price increases, we know demand should go down. So if you're doing a demand-related study, the results you get, are they in agreement with the theory? So that, are the results telling you that if the price increase, what demand decrease? Then another way for you to know whether the model is correctly specified, then it should also, is it exhibiting what we call parameter consistency? Like, for example, if you add some variables or observations, do you get the same results or the result changes? So if you get the same results, you can be sure that your model is good. Also, the model should exhibit what we call data coherence. So in other words, we are saying that the residuals must be white noise. When you say that the residuals are white noise, we are simply saying that they must be normally distributed. That's what we mean by that. Then, just like the other violations of OLS, remember we looked at autocorrelation, we looked at heteroscedasticity, we looked at multicollinearity, and we started by looking at what the problem is, what causes. We looked at maybe the consequences you are likely to encounter if you use or you carry out regression when that problem is present. So then we also looked at how can you detect it, and we ended up by looking at the remedies. So the same way we did that, we'll also do it in these model specification. So I've told you what it is. That one is, for example, not getting the right model. So what are the types of model specification errors? So maybe this one could be related like the causes. So you may encounter or you may experience this model misspecification if you, or in other words, these are the types. If you omit an important variable in the model. Like, for example, you're supposed to have had maybe y is equals to beta naught plus or beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus the error term. But you, in your estimation, you only consider two explanatory variables. So you will have omitted the x3 in that model. So you may likely to have what we call model misspecification, and it is as a result of what we call variable omission. Then another type of model specification error is if you include irrelevant variable in the model. So it's inclusion of irrelevant variable. It can also lead to the problem of model misspecification. Then another one is if you adopt a wrong functional form. So that you are supposed to have like log linear, log level, but you use maybe low level. Like for example, maybe you consider this one, y as a function of x instead of y being a function of ln of x. So this is the correct one, but you pick this one. If you pick this one, you find yourself having the problem of model misspecification. And lastly, another type of model misspecification or model specification error is errors of measurement. This one may arise maybe when you are collecting data. You may collect a wrong, or you may even write a wrong figure, and therefore you may find that the results you are getting are not good because of the measurement errors. So let us look at some of the consequences of you not picking the right model or misspecifying the model. What are some of the consequences you will encounter? One, or let's start by looking at, for example, if you omit a relevant variable, what are some of the consequences you will encounter? So, if for example, this is the right model, plus beta 1, x1, plus beta 2, x2, plus the error term, let's say plus the error term, this is the correct model, eh? But you estimate this one. You estimate this, eh? You estimate y is equals to alpha naught plus alpha 1x. So what can you see here? You see that you have omitted x2 from this model. So where has x2 gone to? You get that x2 will have gone to the error term, because we said that the role of the error term is to take care of the variables which could be affecting y, but they are not included in the model. Eh? So this error term has got x2. So if I was to go back to the theory of demand, assuming this one was quantity demanded, you see quantity demanded is usually made, you can say is a function of, quantity demanded is usually a function of price, plus the error term. From look of things, is the price the only determinant of quantity demanded? You get that we may also be having things like income. Income also affects quantity demanded, but if it's not included in the model, so where is it? It's captured in the error term. So if it's captured in the error term, so if the error term change, do you think also quantity demanded will change? Because inside the error term, let's say it is the income that is there. So if this error term change, quantity demanded will change. Because you have got income here. You remember if you are to plot this, if you are to plot the quantity, this quantity demanded and quantity supplies. So if this one was to, because you see here we have got price and here we have got quantity. So if income was to change, what will happen to this demand curve? Income will shift it outwards. So if it shifts outwards, if it shifts these outwards, what happens to the price? Maybe this was price 1. What is happening to price? Price also changes. And are you saying that price is the exponent variable? So the change in U has also made price to change. So can we say that when the error term changes, also even the exponent variable changes also? So what does that mean? It means that there is the problem of endogeneity, where exponent variable is related with this. So back to our example. In other words, the variable that you omit, you will get that it will relate with the error term will relate with this exponent variable, and therefore when we are interpreting this, how do we usually interpret it? We usually say if x1 was to go up by 1, or x1 was to go up by 1 unit, then y will go up by alpha 1 units. But given that error term also affects x1, can we say this alpha 1 is the effect of x1 alone? So it makes it difficult for us to interpret. So in other words, if you interpret this, you will get what you call biased estimates. So what we are saying, if you omit a relevant variable in a model, the consequence is that you get unbiased estimates. Then also another consequence is that the estimates will be inconsistent. Inconsistent means that if, for example, you increase the sample size, instead of the estimates converging to population parameter, you get that they are even moving away. They do not converge to the population parameter, because we know that if you increase the sample size, the estimates should be coming closer to the population parameter. So those are the consequences of omitting a relevant variable. And also, the last one is the formula for calculating variance will be wrong. If the formula for calculating variance is wrong, you will get that also, you get now the inference testing, you get it wrong, because you will get a wrong t-value. And therefore, even the conclusion you make will also be wrong. So those are the three consequences of omitting a variable. We also call it underfitting the model. So you encounter the three consequences. One is you get unbiased estimates. Also, the estimates are inconsistent, and inference testing is invalid. So let us look at some of the consequences of overfitting a model. We call it including an irrelevant variable. Let us see the consequences you will encounter. So, if this is assuming this is the right model, y is equals to beta naught plus beta 1, x1 plus, or just this one only, plus the error term. And you estimate this, y is equals to alpha naught plus alpha 1, x1 plus alpha 2, x2 plus the error term. What have you done? You have included an irrelevant variable in this study. This is the correct model, but you have picked this one. So you will get that this one, the consequences are the estimates will be unbiased. Now this one is better because it doesn't touch on the unbiasedness of the estimates. So the estimates will remain unbiased. They will also be consistent. The problem is only in the formula of variance. Do you still recall the formula of variance? Yes. We agreed that variance is given by, so if for example it was variance of alpha 2, we agreed it is given by this summation. This is the variance, how we get the variance. Even though you can get it from, you remember the model of this. You remember this model? Yeah. X1, x2, summation of x1, x2, summation of x2 squared. We agreed that if you get the inverse of this, this was the beta, not beta 1, beta 2. Of course, you get this the inverse. So we agreed this is beta, not beta 1, beta 2. We agreed that the principal diagonal gives us the variances, and the others gives us the covariances. So if you are to get variance of beta 2, we agreed where the 2 intersect. Beta 2 is here, beta 2 is here. So you pick this one. And given that it is, you see when something is raised to negative 1, alternatively you can write it as 1 over. So that's why we are saying, but remember we usually put sigma outside here. Remember the formula. So if you are to pick, so this means that this is the variance of This is the variance of, or, now for you to understand it better, the variance of beta 1, the variance of beta 1, how will it be? The variance of beta 1 will be sigma squared over summation of x1 squared. I think that if it was the correct model. But you look at the one you have. You've got more exponential variable. So you remember when we are discussing multicollinearity, we said that if you have got more variable, then the formula changes. So you get that the variance of alpha 1 will now be the same as this one, sigma squared over summation of x1 squared. But the moment you've got more exponential variables, you need to add the variance. You remember this r squared of x1, x2. You remember this one, we call it variance inflating factor. If you have got more than one exponential variable, the formula for variance changes. Now, how do you get this r squared? This r squared, you want to see whether x1 and x2 are related in a way. So you make like x1 the subject of the formula, and then you run it on x2. So this r squared is called auxiliary r squared. So when you get it, assuming there is some slight relationship between x1 and x2, of course, you people, you know the range of r squared. It ranges between 0 and 1. So let us say the relationship that is there, maybe the r squared is 0 point. So this one, we can say this one is maybe, let's say our variance is 2.4. But when we included another irrelevant variable, what will be the variance? The variance will be still 2.4, at least multiplied by something extra. So let's say, for example, the relationship between x1 and x2, the r squared we get maybe 0.4. Let us see what will happen. You see it will be 2.4 times 1 over 1 minus 0.4. Down here you get 0.6. So 1 over 0.6 is something like around you'll get 1 divided by 0.6, you get 1.66. So you see, the original 2.4, because of you including an irrelevant variable, now the new one is 2.4 times 1.67. What I'm saying, this one will be a little bit large. Maybe it may be like, maybe it can be like 3. So what we can see is that if you include variable, extra variable irrelevant, what you're doing is trying to get a larger variance. But reflect, where do we use variance? We use variance when we are, remember we use variance to get standard error, and standard error is used in the formula of getting the t. Remember the t? T is usually coefficient divided by standard error of that coefficient. So you get a big standard error. Then what are you likely to get if you include an irrelevant variable? What is the final t? Because it's like you're dividing a number by a very large denominator. What do you get? T is likely to be small. So in other words, you may end up getting t value that is less than 2. Isn't that? So are you seeing the consequence of including an irrelevant variable? You end up maybe getting wrong in inference, or wrong t value. So those are the consequences of model misspecification. Then how can you test of model misspecification? How would you know that your model is misspecified? How can you test? So just like the same way we did, the same way we looked at multicollinearity, heteroscedasticity, and also even the autocorrelation, we have got the informal ways. So what you can do, let us start, for example, if you assume that you have included or if you think you have included an irrelevant variable, how can you test it? Let us start from there. You are assuming that you may have included a variable that you're supposed not to have included. So how can you go about it? So the first thing to do, assuming this is the model, so you want to see, to test, assuming this is the model, you consider this model. But in your feeling, you think that X3 should not be there. So what you need to do, you start by like stepwise regression. You start by carrying out beta naught plus beta 1 x1. Of course, when you do this, you'll get some results. Look at the results. How are your results? Look at your coefficients. Is your coefficient good? Good in terms of maybe, are they statistics? Look at the R squared. Is your R squared good? If it's time series, you see R squared should be 50% and above. What about the Durbin-Watson statistic? If the Durbin-Watson statistics is 2, you remember when we looked at autocorrelation, we said 2 is good. If you get 2, it means there is no autocorrelation. So if you run these, and you get now those statistics I've just told you are not good, continue and include the second variable and observe now. You see, you can include the second variable and you get, oh, your results are now good. F statistic is best, and of course you know when probability of F is good, maybe less than 0.1. F, probability of F. You remember probability of F, we test using the three levels of significance. You see at 10% is like 0.1, 5% is like 0.05, 1% is like 0.01. So when you are testing F, you get F is less than 0.1. You see that one is good. R squared is maybe like over 0.5. That means 50% and above. So if you get your results are good, Durbin-Watson you get is true. You stop there, you don't add X3. Then you say the correct model is now having only 2 exponent variables. Isn't that? Now, my friends, then I want us to see how you can test using, assuming you think you have omitted a variable. How can you test it? So I hope everybody is okay with testing for variable or testing for inclusion of irrelevant variable. I've told you how you can test it. That one is like stepwise. So what about if you think that you may have omitted a relevant variable? How can you test it? What you need to do is the results you have, look at them. How do they look like? So you may get that the results you have, they are even in disagreement with the economic theory. Maybe you expected like a negative sign, but the results you have are giving you negative sign. Maybe you have got something like this. You have got y is equals to beta naught plus beta 1, x1 plus beta 2, x2, then plus error term. But you feel like you have omitted a variable. And how would you feel like you have omitted a variable? Because maybe the results are not good. This sign you expected it to be positive, maybe you have got negative. This one you expected to be maybe negative, you have got positive. You look at even the coefficients, significance of the coefficients. You get the t values are less than 2. You see, if t values are less than 2, it means they are insignificant. The coefficients are insignificant. You look at the F statistic is not good. You also look at the Durbin-Watson. You get Durbin-Watson is around close to 0, 0. See, if it is close to 0, it means there's autocorrelation. So maybe you can try to ask yourself, could you have omitted a relevant variable? So what you will do, you will try to add Because you see, when you carried out literature review, you may have come across many variables. So try to get one of the variables you got when you are reviewing your literature. Bring it on board. Then you see how your result will be. So you can now try to add so my friends, when you add another variable x3 and you get now the results are good, so it will be a pointer that you may have left an important variable, and therefore this could mean that you misspecified the model. So by introducing this x3, then the results now become good, the signs are good, the t-value is more than 2, the f statistic is less than 0.1, the the Watson statistic is around 2. Then you say, or 1.98. Then you say, oh, I had omitted a very important variable. So that's how you can test for variable omission. So we have looked at how you can test for inclusion of irrelevant variable. If you feel like you have included an irrelevant variable, how you can check. We have also discussed if you feel like you have omitted a relevant variable, again how you can test it. So I hope that one is clear. Then, but the problem with this is, or could there be any other way you can be able to do this? Could there be another way you can be able to test other than those? Just testing is like for general, if you have omitted. Could there be, so it's like, is there any formal test you can use to test for variable omission? So this one will take us around 5 minutes just to delve into variable omission a little bit, because we saw that one is the one that has got serious consequences. So let's see. Assuming this is the right model, y is equals to, let's say beta naught plus beta 1, x1 plus beta 2, x2 plus the error term. But you go ahead and run these. You see, this is like the formal test. You run these alpha naught plus alpha 1 x1 plus the error term. I hope everyone understands now what we understand what we mean by this, or what is the implication of this. Where will x2 be? It's now captured by the error term, and we saw it. Initially I had indicated that if that one happens, you will get that this one, the x and the error term will be related. Remember we looked at it. So what you need to do, you will get that if you try even to get a D, Watson, you will get that the Watson for inside model will be between 0.7 to maybe 1.03. 1.03. Are we in agreement there? You will get DW to be between 0.7 and 1.03. What does this imply? If you get DW of 0.7, what does that mean? You see, it's closer to 0 than to 2. So it could mean that there is autocorrelation. But what is autocorrelation? Autocorrelation is where the error term, the current error term and the preceding error term are related. But this is not the case. If you get this, it may not be implying that it is autocorrelation. This one could be an implication of model specification, or model misspecification, or model specification error. So Watson can be used to test for two things. You can use it to test for autocorrelation, or you can also as well use it to test for model specification. So I want to bring to attention how this one is used to show model specification error and not autocorrelation. Now, my friends, this error term, this U here, you'll get that this U, inside here, it's also taking care of the X2, which we had left out. But you'll get now, so in other words, we are saying this error term U, can we say error term U is, it has got the usual error and X2. You can notice that. And what is autocorrelation? Autocorrelation is where the current error term is related to the preceding. But in time series, if you have X2, which is in the error, you see autocorrelation is a problem in time series. Sometimes observations in time series are likely to be related as you go into the future. You'll get, like, for example, if you are using your data from 1990, 1991, 1992, 1993, 1994, you can get that in 1991, maybe the figure is like 2. In 1991, you can get like the figure is 4. In 1993 or 1992, you can get the figure is 8. In 1993, you can get the figure is 16. So it's like it is being multiplied by 2. So you get, it's like whatever that is the error term, the error term of 1990 and 1991, they seem to be related, but it's not because of the actual error, it's because of the X2 that is inside the error. So that would be saying it's impure autocorrelation. The usual one is called pure autocorrelation, but this one is called impure autocorrelation because it is autocorrelation not because of the error, but because of the omitted variable that is within the new error term. Are you seeing that? So that's why when you test, you will find that the D value is, the DW value is 0.7. So this one is an implication of impure autocorrelation or serial correlation. And this one is caused by the errors not being related, but by the exponent variable that is there in that error that are being related. So if you get this, it could also be implying that your model is misspecified. Because if you correct and you test for autocorrelation, you get that autocorrelation is 2. Sorry, you get that this DW is 2. What does that mean? It means that no autocorrelation. Because you see, by correcting, how are you correcting it? By removing the exponent variable from that error and letting it be on its own. Then you will get that now W what's on is 2. So D, if you get D, sometimes it could be meaning that there is autocorrelation, and in other cases it could mean that there is model misspecification. So this is the theory behind what we call the test of variable measure. It's called Ramsey reset. Ramsey reset test is used to test for whether you have omitted a relevant variable or not. So the Ramsey reset is anchored on this argument. So what will you do? The best thing to do is, because here you may have very many variables. You see, of course, here I've used one. But now, what you can do, you can simply test whether to see if the error term and the exponent variable are related. Because you remember when I was explaining the case of what is demanded and price, I told you that now income is inside now the error. Income can push the quantity demanded outside, and therefore the price is also pushed upwards. Are you seeing that? So the same applies here. So it means this one and this one may be related. Are you seeing that? So what you will do, you will get this. This one is called estimated. Of course, you remember we agreed that y can be the same as y hat plus now u. You know something like that? This is now the estimated y. Everyone knows how we get this. Because once you have got your model like y is equals to, assuming you had this y, you had x. you can be able to estimate, assuming you get something like 2.4 plus 3.2, you can be able to get y hat. I believe everyone knows how to get y hat. So once you have this, you can plot it, y hat against you and observe what happens. If there is a systematic pattern, then it means the error term and the exponent variables are related. Are you seeing that? They are related. They are related. So, and if they are related, it means there is likely that there is model misspecification. So, this one is now the theory. That's where Ramsey reset test is anchored on. So, Ramsey, what they say, what these tests indicate. This test assumes what? So you run this model. So you just run this model. You see, when you run this, of course, my friends, you will get R squared. You can call it R squared old. Then you run this one. It's like when you plotted and you found there was a systematic pattern. So the best model could be, you include this squared, you also include this cubed. So this one is now like the new, this is like the new model, the one that now, so these ones they take care of the variables you feel like you may have omitted. I see that. So we are saying this one is now the correct model and not this one. So you see, when you estimate this one, you also get R squared. We can call it R squared new. So and then the question is, how would you go ahead and carry out the test, the Ramsey reset test? So the Ramsey reset test is an F test. So how do they calculate it? They say F calculated is equals to, you get R squared new minus R squared old over n. N is number of the new exponent variables you have included. Like in this case, our n is, n is sample size. This one we can call it, or we can just call it number of new exponent variables. We can call it number of new explanatory variables over 1 minus R squared new, everything over n minus number of parameters in the new model. Are we in agreement there? So how are we doing it? We are saying it is F calculated equals R squared new minus R squared old over number of new exponent variables. Like, what can you say about new exponent variables? There are how many? 2. This one and this one. So here is 2. What about n? N is, you'll be given number of observations you had. Then what about number of parameters? Now, this number of parameters in the new model. In the new model. So like in this case, number of parameters in the new model is 1, 2, 3. So my friends, after you have done that, you see this gives us F calculated. I did tell you the null hypothesis for this test. The null hypothesis, what is the aim? The aim of carrying out this Ramsey reset is like we are assuming there is variable omission. So, and you see the null hypothesis always negates what we are thinking about. So, because as we are thinking that we have omitted a certain variable, so the null hypothesis for this test is that there is no variable omitted. So, null hypothesis is no variable omitted. Then alternative hypothesis is there is variable omitted. So once you get this F calculated and you you get F critical. How do you get F critical? F critical, to get, you see F critical, you need 0.05, for example, or 0.01, or 0.1. You see the levels of significance, 10, 5, or 1. And now, F has got also V1 and V2 degrees of freedom. So what is V1? What is V2? So you get V1 is usually what is up here. So V1 is the number of explanatory variables introduced, number of new explanatory variables. And V2 is the n minus number of parameters in the new model. Are we in agreement there? So once you get your F calculated and you get F critical, the next stage is for you just to compare the two. If F calculated is greater than F critical, you reject the null hypothesis. And therefore, if you reject the null hypothesis, what does that mean? If you reject the null hypothesis, it means that your model has omitted a certain variable. And therefore, what should you do? You see, it's like you have been informed that you have omitted a certain variable. So the remedy is for you to go back maybe to the literature and check which variable you may have omitted, and you try to include it, and you test the Ramsey reset test again, and see now whether the results will be good or not. Are we in agreement there? So, usually in Stata, or maybe even R, you may not be going through this. There is an inbuilt test. The Ramsey is there. What you need to know is the command for Ramsey. So if you are doing a research, the first thing to do is to carry out your regression. You just say regress your dependent variable, then you include your explanatory variables. So then you press enter. Immediately you do this, then you write omitted variable test. You just write OV test. Once you write OV test, it will give you the F. But if you don't have the table with you, you can use the probability of F. Probability of F. You see, I told you if you don't have table, sometimes you can be using probability to test, even if you can test if the results are good. So usually the threshold is 0.05. So if the probability of F, the test gives you, if it gives you like 0.04, you see that one is less than 0.5. It's less than 0.05, using that. So if it gives you 0.04, it means that you should reject the null hypothesis. And therefore, if you reject the null hypothesis, it means that there is variable omission. But what about if it gives you like 0.06? You see, if it gives you 0.06, that is greater than 0.05. So it means that you do not reject the null hypothesis, meaning that there is your model is good. You have not left any variable outside. So that is the discussion on model specification. Yeah, but of course you can also visit a learning management system for notes and any other econometric textbook for more information. Thank you so much.